Hello again. We only have a couple laps left, so it's gonna be a final stretch of marathon. And I hope you are staying connected or staying on the top of the course material, as well as also make sure in the lab video what you have studied or learned so far, make sure you apply that for your final project as well. So like work along with your final project as you learn in the labs. Okay, so let's look at the let me share the screen first and begin today's lab. So what you learned in the last week, let me first clear my global environment. uh, all right, so what we learned in the last week, let's apply that. How you can apply for your final project. Let's connect the dots. uh, First of all, let me uh, load the library packet that I need for the data. All right, uh, let's create some variables first. ID, SCS, age. Again, you already know the drill. And let's create the data set using the data frame. We have the 10 observations. Let's look at the data first. ID, SCS, and age, right? Uh, so this is what we have. Now let's create the frequency of SCS, socioeconomic state. So you know that you do that by table argument. Okay. So we have 5 levels: 3 high, 1 low, 2 low, medium, uh, 2 medium, and 2 medium high. Okay, so these are the levels we have. Um, Now let's create, if you're interested in examining the SCS and age, let's create a ggplot. Which plot do you think would be the best? Let's go with the box plot first. I'm not going to explain now this code because you should know that by now, right? We already covered that how to build the plots using ggplot. So it's the same system or mechanisms. Uh, Now this is what the plot looks like. Uh, so we have high, low. Why do you think it's only one single line here for low? Socioeconomic status and the age. Uh, and you can obviously, I'm not going to go the interpretations because it's just a random data that we have created, right? So, uh, but you can see that the rest of the boxes, but the low is only one. Why? One line. What does it mean? So that's because, as you can see the tables, the frequency distributions, there is only one participant that falls in the low. That means that data itself is a mean, it's a median, it's a mode, and everything there. So that's the reason why you see single bar there, right? So that and this is where and I say, like, when collapsing the data sets, you lose some power, but sometimes it becomes important to collapse some of the categories for easier interpretation. First of all, and the second also, when the frequency distribution is extremely low in some levels of a categorical variable, like here, like for instance, it's only, there are 5 levels of SES, and this is a hypothetical data again, but just like having only one participants in this category, it will create some issue when you build the regression models. So like for instance, if you have a variable with 6 different levels, and in some levels of that categorical variable, if you only have 2% of the data, 3% of the data, that's too low. You might want to collapse that with some other category. Okay. uh, and that will help you better examine the uh, exposure and the outcome. So how do we do that? Again, just connecting the dot. Remember what we applied there in the previous lab, or what we learned in the previous lab. Let's apply that. So you can change the observations within a variable. So I want to collapse low, medium with low. So how do we do that? So I can say low, medium, as I said, specify the data set, specify the variable, and then you can specify that you want them to be recorded as a low, and you want to be record the medium high as a high, the same process, and you run that. Now let's view the data set again. As you can see now, it's all you see is the medium, low, and high. And now let's create the table again. So we have 3 highs, which should make sense because, and I always tell you the number before and after, just to make sure that you haven't made any errors. So we had the 2 highs. Uh, Sorry, we had the three highs. That's what we have, three, right? We collapse the medium high and the medium into the medium. So the medium and the medium high, we recorded that. So that should be 4. So that we have 4 mediums, and the low should be low and low medium should be 2 plus 1 3, right? 2 and plus 1 3. So that is correct as well. And now let's examine that. So now that worked properly, and now let's recreate the plot. Uh, and that's where you can see low, medium, and high SES versus age, right? So when you work for a final project, and this is what the application means, this is a hypothetical data. But if you're a categorical variable, one variable with 5 or 6 categories, or even 3 or 4 categories, where some of the labels in that category it's extremely low, like 1%, 2%, 3%, feel free to collapse them. I think you should collapse them so that will help you better make the regression models. Okay, so this is what the application of what we learned in the last lab. So like for instance, as you can see, we changed the data set, recorded some observations within a variable, right? We obviously did not transform the data, uh, but then also it helps us creating the plot as well, data visualizations, and that's creating more rigorous analysis or the more meaningful analysis. Okay, so let's go this week's. So hopefully that gives you some idea how you can apply that in your final paper. Uh, let's go for today's lab. I'll clear the sessions first. Let's we'll continue with the data transformations, and then we'll run some correlation tests and the t-test. So stay tuned. There we go. I'm gonna start here. Okay, let's run the ID. HG means mercury. Let's just assume I want to create the data sets where I want to examine the association between mercury concentrations and ADHD, attention deficient hyperactive disorder. So let's just see if I want to create that. So these are the concentrations of mercury at the 12 weeks during pregnancy. Okay, these are the mercury concentrations at 28 weeks during pregnancy. These are the mercury concentrations at the 1 year. These are the child mercury concentrations, the sex of a child, and the ADHD score. Okay, let's just create a data frame using all those variables. So this is what your data frame looks like now. So ID, uh, mercury concentrations at 12 weeks during pregnancy, so prenatal mercury concentrations at 28 weeks, and this is the child postnatal concentration at one year. When the child became 1 year of age, then you take the blood, and these are their child's mercury concentration. This is the sex of a child, and this is the ADHD score. Okay, just again hypothetical uh, example, but let's use this data. Now let's just assume I want to. This is what the data set is, and now, but what I want is that create a box plot where I want to plot mercury concentration on horizontal axis, like the 12 weeks, 28 weeks, and 1 year, and ADHD score on the y-axis. And so this is what I want to create. Is for instance is if this is what the plot is. Oops. This is 12 weeks during mercury concentration. Let's assume this is the box plot. Please pardon my. This is the 12 weeks. This is what other week was that? 28 or 26 or whatever it was. 26 weeks. Let's just assume this is the box plot. This is the 1 year mercury concentration box plus. I want to see which levels are more meaningful and is associated with ADHD, prenatal, postnatal, or which part, even if it's prenatal, early week pregnancy or the late week pregnancy. I want to see with the ADHD score on the y-axis, and I want to examine that, for instances, mercury concentrations with ADHD scores. Or let's just say if you want to create just on just a horizontal axis, you just want to create the uh, compare the concentrations of the mercury on that, right? Not the ADHD scores. Let's just say we'll figure out that later. But let's just say if you just want to examine the mercury concentration, you just want to plot them on the one, and you just want to see which concentrations are higher, which concentrations are lower, and in that sense. So in order to create this, like how do you create the plot, something like this? The challenge here would be, oops. The challenge here is because there are three variables. Mercury is recorded in three different variables. That means that in on the horizontal axis, you need to specify three variables if you want to have all three in the same plot, in the same on the same axis. Now, when you create a plot ggplot, you only specify one x variable and the one y variable. Unless you go for three dimensions, you can have two vertical axes and one horizontal axis, but that's still not going to solve the problem. So how do we do that? So remember, this is what we call as a wide data set, and this is where the data transformation comes in. So what you can do, or what we should do, is that we should create a one mercury variable that should have two columns. One column will have the mercury concentrations 12 weeks, 28, 1 year, and so on, and here the second variable will have the concentration listed right by it. So how do we do that? We can transform the data set from wide to long. So how do we do that? So first of all, for in order to do that, you need to use the reshape 2 package. So make sure you have installed the package, and if that is the case, make sure you load that package to use that. So to melt the data set from wide to long, what you need to do is that specify that. Remember, this is the new data set name that I want to save that as. I'm telling the R to melt the old data by ID. Remember, you always want to do by ID, right? So let's keep that. I here, that's the data sets. We have 5 observations, 6 variables. That's the original one. Now we are going to run this, and we have the data underscore long, which has 25 observations with 3 variables. Let's look at the data now. So this is what the data set looks like now. Now we have IDs, and by ID I have their concentrations. So these are the 12 weeks concentrations in the value, and so on. Again, the 5 participants again, but that's the concentrations 28 weeks and so on. So now what you can put is that on x-axis you can have this variable, on the y-axis you can have this value. Make sense? So that way we will have the plot on the x-axis, the mercury concentration, y-axis their score. But the challenge here is that when we melt the whole data set, it also melts the sex and ADHD variables as well. Now that's a problem, because that doesn't when you plot the variable, it's also going to plot the sex and ADHD on the same scale, which should not be the case. In fact, we want these two variables separate if you want to examine that exposure and the outcome as well. So this melted the whole data set. So how do we address that? So you can specify exactly which variables you want to melt in RStudio. So here what you say is that, again, the same data underscore long, you melt, this is the old data set. You can say ID variables is equal to ID. So you want to do that by ID, but you will here specify measure dot vars. You specify what variables you want to melt. And here you just say, I just want to melt the mercury variables. Once you run that, as you can see now, you have 15 observations and 3 variables, right? So as you can see now, uh, you have the variables and the values, and now you do not have the sex or the ADHD score. So now you can easily plot variable on your x-axis and the value on your y-axis, and your plot is ready to go, right? So you have the intended or desired plot. Now, as you can see with the previous code, we have the default variable names that are assigned as a variable and value. But what if you want to specify name yourself? You can do that as well. So you can just here you will just specify variable dot name is equal to, let's just say if you want to put here. So this is what I'm talking about. So here the variable and the value, those are the default names that the RStudio give, because we didn't specify that. But you can name this variable, and you can name this variable as well. So I can say these are the mercury concentrations. So I want to specify that as a Hg, and the value I want to specify that as a blood levels. These are the blood concentrations for that. So once you run that code, uh, and once you view that data set again, I have the variables recorded as the names that I desire to have. Okay, but also, like, the challenge here is that we have the 3 variables, but we lost the data on sex and ADHD. Now that might not be meaningful as well once you meld the if you meld the data too, right? Because sometimes some analysis states, some regress, some plots, you may need to have your y variable as well, or the important confounders. So what if you want to melt only 3 variables, but then also keep the sex and ADHD as well? So you can do that by melt ID variables would be the ID, sex, and ADHD. So now you're saying that melt that, but keep this one as it is and meld them by these variables. So once you run that, as you can see now, you have 15 observations and 5 variables. And as you can see now, we have the ID, their sex, ADHD score, and then we have the mercury concentrations and also their mercury, the time point of the mercury concentrations, and their blood concentrations here as well. So now you have ready to go. This is the whole complete data sets that we have melted on specific variables, but they kept the original as it is as well. Okay, and again, why do we want to do that? Because in order to create certain data visualizations, certain graphs, if some, like for instance, if this is your original data sets, it may, and if you want to have the mercury concentration, like for instance is, if you want to build a regression model where your exposure variable is mercury concentrations with 3 different levels, this is not going to help you because these are 3 different variables, not the categorical variables with 3 levels. And this is now here your exposure is a 1 variable with 3 different levels. Make sense? So depending on the test, depending on the type of the data, you may want to do that. So that's option number 1. You can also do that by using the tidyr package as well. But because those are the conflicting package, we have to first remember, we have to first detach the reshape data that you use. Okay, so let's detach that with with this code, and then load the tidyr. Again, if you haven't installed, make sure you install that as well. Okay, so here what how you, this is the option number 2, right? So let's see how this works. Here we use the melt function with the reshape package. With tidyr package, it's a gather function. So what you're saying that you gather the data from, this is the old data set name, and I want, this is the new data set that you want to save in. So I'm saying the data underscore long 1. Okay, that's what you are specifying that in. So this is, I want to save this new data set in data underscore long 1. You are saying this is the data. Okay, these are the mercury and the blood measurement, that's names that you want to assign. Okay, and which columns you want to meld is that you want to, I want to call, I'm telling the art that I want to meld the columns from 12 weeks. This means that from 12 weeks to 1 year. So when you look at the original data, so 12 weeks to 1 year, so it's going to melt these 3 columns. And this would help, let's just say if you have like 10 different columns that you want to specify that, and then you can just say first and the last one, and it melts the whole ones in between as well. Okay, so this is what the code is. And you want to specify them as a factor variable, so you say factor underscore key is equal to true. Let's create the data underscore long 1. And again, as you can see, it's a 15 observations and 5 variables. It only melt the three variables that I intended to, kept the sex and ADHD as it is, and with the ID too. I didn't need to specify that. It automatically did that, left the rest of the variables as it is, right? And that's the reason why, as you can see, that the previous data sets and these data sets are exactly the same using 2 different library packages. You can also specify the column names that you like to melt as well, rather than just using, because if they're not in sequence, then you can specify the column names as well. For instance, you can specify that's the HD 12 weeks, 18 weeks, 1 year. If they're separate, you can do that as well. More than 3, more than 5, it doesn't matter, right? You can run the same code, it gives the same observation, same the data set. And now you can see, if you want to create the box plot, you can see the box plot, and this is what I wanted to have initially. Mercury concentrations and their blood measurement, mercury concentration time point and their blood measurement, right? The blood concentrations there. And you can see now the trend easily on one single plot. Make sense? So this is why you may want to melt your data set. Now let's just say, what if you want to not melt? What does it mean? Let's just, what if you want to convert the long data into the wide data set? Let's just say if this is your data set, if this is the data set, but I only want to examine the 12 weeks one as an independent exposure variable, 1 year as an independent exposure variable, and 28 weeks as an independent exposure variable. Now, one way to do that would be obviously subset the 3 different data sets from this one and examine the 3 different data sets separately. Or you can just widen that data and then use the variables whenever you need one. Okay, so option 1, again, let's look at we already have the tidyr package, so let's look at with tidyr. We already have the datasets library package ready to go. So you can widen the data, saying that here it was a gather, with a tidyr, but here you specify as a spread because you want to spread the data. So you are saying that spread this data underscore long, this data, let's just say I want to spread this data, spread this data, save that as a data underscore wide, uh, and which variable I want to spread here, the variable this column and the value this column, because it's just a sign that it is. I'm telling the R to, because remember these variables are not melt one. These are not the melt one. These are the melted ones, right? That I want to widen it. So I'm saying that I'm saying the R that spread this variable and spread this variable as well. So the variable and the value. So you're telling that R, once you run that, let's look at the data underscore wide. Remember? So now these variables are spreaded. As you can see, it's exactly it. We came back to the original data sets that we had, except for the just the change in the sequence of the variables. Make sense? Same variables. So that's one way to do that. You can achieve the same as with the reshape package as well, reshape 2 library package as well. Let's detach the tidyr first and reload the reshape 2. So here what you're saying the R is that we want to keep ID, sex, and ADHD as it is separate. And then variable is the column that we would like to widen, and the value should take place as the observation. So how you write the data set is that here it's a decast function. So this is the, I'm telling the R to widen this data underscore long. So spread this data where I want to keep ID, sex, ADHD as it is, but then spread that by this data, spread this variable. So that's a mercury concentration one, as you can remember. This is the variable, right? Uh, and observations of this value are the column that is labeled as a value. This is the blood concentrations, right? So once you run that, data underscore wide underscore one, as you can see, we achieve the same thing, original data set that we had at the beginning of the lab. Make sense? So that's the second way to do that. So for instance, if it's a data underscore long underscore one, you can just specify the data underscore long underscore one, and then you can specify the here the instead of variable, because here the name is given as hg, you just specify that hg, and then here it's a blood measurement. So you can just specify as a blood measurement here, right? Uh, and then you run that, for instances, it will give you the same data set. Make sense? So that's I hope that's, rather than variable and value, it helps you understand what we did here. Okay. So that's where you melt the data set or spread the data sets using the two different library package. There are two options: tidy or reshape2, whatever works best for you. Feel free to use that. But sometimes be innovative, think creative. Sometimes you may want to do that, you may not want to do that if your data set is in perfect shape. So you may not always need it, but if you need it, this is the way to do it. Okay, so I just wanted to introduce that. That's part of the data transformations and data cleaning. Now let's go quickly. Now that's, remember, so far we have talked about uh, now we have talked about how to transform your data, how to clean your data a little bit, uh, like how to subset your data set, how to change the variable names, how to change the observations within a variable. So you know all those data cleaning, data transformation. So now you should have your data set ready for a final project. Then data visualization, we already covered that. So if you want to make some changes to your variables, collapse some categories, we talked about that in today's lab as well. So make sure if you're in your final project, if there are variables that needs to be collapsed, make sure you collapse them and rerun the data visualization. And now let's go to the univariate analysis. I will introduce that, and then we'll go to the regression part later on. Okay, so for univariate analysis, in the theory we have talked about so far t-test and we haven't talked about the chi-square or nova, but I'll try to cover that in the lab. Uh, but let's start with the t-test and the correlation coefficient, right? So first we start with the, so this is what the process of your final project should look like. First, you transform your data if it needs to, clean your data, clean some of the variables that you have selected, run the descriptive statistics, okay, uh, check the data visualization, okay, then conduct the univariate analysis either with t-test, chi-square, or ANOVA, okay. Then run the regression correlation coefficient for continuous variables, uh, and then go to build the regression models. That should be the process. Okay, but let's and that's a brief process. But again, that depends on the choice of the variables and so on. But let's look at first the correlation coefficient, because that might be the fresh in the mind. As per the last lecture videos, because the t-test we covered a little bit before. But let's go with the correlation coefficient. Remember, it takes longer to prepare your data set, but once your data sets are ready and prepared to conduct these tests, univariate analysis, correlation coefficient, regression models, they are very quickly and easy to do it in our studio. It's just that to getting ready your data set, it's the longest things to, or the most time that the people need to spend. Okay, so now let's assume your data set is ready to go, and I want to examine the correlation coefficient between the 12 weeks mercury concentrations prenatal, so during pregnancy, and ADHD score, and see if I want to examine if the, so my exposure here is a mercury exposure during pregnancy, and I want to see if that is associated with the child's ADHD scores. So how do I do that? So remember, when do we do the correlation coefficient? Check theory lecture. Why should we use that? Check theory lecture. What are the interpretations? Check theory lecture. What are the limitations of correlation coefficient? Check the theory lecture. Okay, so make sure you watch the theory video as well. But how do we examine that? So here it's very easy to do that in R. So what you just specify is the correlation. So you just say core. You specify that this is your x variable, which is in. So this is a variable name which is in the data set underscore data. So that's the data. My data is that. So data dollar sign. This is the x variable data. In this data set, there is ADHD, which is my y variable. So the first x variable, y variable, and then I'm saying that I want to have the Pearson test. You can change the method as well. But again, it just for if you have the ranked data, then you might want to use a different method. Uh, Spearman. But again, we are just going to stick to Pearson for the purpose of this course. Okay, we talked about that it's in your theory textbook. If you need to, then it's pretty easy. You just change the method in here. Just one single thing. If you need to change that, it's pretty easy to do that in our studio. So if you have that data that requires the other method, I just demonstrated you for those students as well here. You just change the method, everything else stays the same. Now let's just say if you run that, it gives me the correlation coefficient between the prenatal mercury concentrations at 12 weeks and ADHD scores in children is 1. What does it mean? What does it mean when the correlation coefficient is 1? If you're saying that it's a perfect positive linear association, you are absolutely correct. Okay. Uh, Again, go back to the theory for interpretation and so. But the problem here is that does not give us a significance level. I'm not sure if this is statistically significant or not, or it doesn't give me the confidence interval either. So one way to do that is that rather than just using the core, we specify that core dot test and then have everything else as it is. And I'm saying that examine that at the confidence level of 95, 0.95. So I want to have the, so that's, remember the alpha error, we talked about that, right? So you specify your alpha here with the confidence interval. So once you run that, and that's where you get the whole test on the correlation coefficient. Okay. Now, what is the t-test statistic here? And again, if you don't know that, you might want to go back to the theory lecture. We talked about, when we talked about the correlation coefficient, we talked about the hypothesis testing of correlation coefficient, right? Remember, what was the null hypothesis there? Yeah, the null hypothesis was the correlation coefficient, population correlation coefficient is equal to 0, right? When it is equal to 0, what does it mean? No association, it's a flat line, right? The alternate hypothesis, and that's why if you don't know it, it's written here as well. Our story is pretty good. It also has written to the alternate hypothesis where you say the true correlation, so it means the true population correlation is not equal to 0. That's what your alternative hypothesis is, and this t-test is for that alternate hypothesis. So just by examining the t-test, the test statistics, you can see that it's obviously going to be significant. It's so high, right? With 3 degrees of freedom, and this is what the p-value is, right? And again, we learn in manually as well how you can examine the t-test using the t-table with the degrees of freedom. So you can do that as well, but the R gives you the p-values right there as well. So it's less than 0.001. Obviously, it's highly statistically significant, strong. strongly significant, right? The 95% confidence interval, because we specified the alpha here, because we want to have the 95% confidence interval alpha 0.05. So that's where you can see, as you can see, the confidence interval here is 1 to 1. Again, it's because it's remember, look at the data, like obviously, uh, 12 weeks concentrations, 11, 12, 13, 14, 50. ADHD were 71, 72, 73, 74, and 75. That's why you see the perfect positive linear association. And it is a hypothetical data. That is the reason why the confidence interval is 1 to 1. Why it is 1 to 1? That means that we are highly confident in our results that the correlation, true population correlation coefficient is 1. You will not find that in the such precision in the real life data, but this is just a hypothetical sample. So that is the reason why you see that. But this is your confidence interval, and the confidence interval also does not include zero as well. If you can also look at just the confidence interval, and it does not include zero. It does not cross zero. That is the reason why also you can say it's statistical significant as well. And this is the regression, that's the coefficient here. It gives the sample estimate. Remember, this is for the population data. Remember, what does the confidence interval mean? What does it mean? How do we interpret the confidence interval for correlation coefficient? Is this for sample or for population? If you're thinking for population, you're correct. What is the interpretation? I will not give you the answer right away. You need to go through. If you don't know that, make sure you watch the video on the confidence interval and the interpretations of the confidence interval. Okay, and make sure you interpret. So, like for your final paper, when you run this test, for your final paper, between your exposure and your outcome, if both are continuous, and if you're running this correlation coefficient test in your final paper, I want to see how you in your results sections, when you describe your results, make sure you explain all these like I explained here. uh, like look at the, like, what does this confidence interval means, like how to interpret that, how do you interpret these numbers, if it's statistical significant or not. Okay, and this is your sample correlation coefficient for your sample, and it is one, right? You can also say, I hope. So this is how you run the correlation coefficients. Very easy, right? Very quick. uh, but they remember the running the test, it's is as important as how you interpret that as well. Obviously, interpretation is even more important, how you correctly interpret that this number. So make sure you learn the interpretation that comes with it as well. uh, you can also, interestingly, in just like our studio, it's so powerful, you can also save the results in an object as well. So let's just say, if so, remember, this is the same. So I'm saying running the test, but I'm saying that is this test in the object called core underscore result. So let's run that. As you can see now, I have the core underscore results in here. When you click on that, it will not make sense to you, but hold on. Why do we want to do something like this? So when we ran this test, like without saving in an object, it gave me this whole uh, results in together, like the Pearson's product moment correlation, right? It gave me the whole results. But when you save that in your object, you can specify what exactly you need. So let's just say, just like in a data set, you specify with one variable within the data set, the same thing within this object, I just want to have the p-value. Once you run that, it gives me the p-value, only p-value. If you just want to have the estimate here, the correlation coefficient, you can just have the correlation coefficient estimate. If you just want to have the confidence interval for this estimate, what you see here, you see there is a confidence interval that you have here, right? And it does say it's a 95% confidence interval, and this is the interval is. Remember, when you write that in your final paper, always like write that the correlation coefficient between the exposure and the outcome is 1, and in bracket always specify 95% confidence interval 1 to 1. Never just put the coefficient without the confidence interval. Confidence intervals are very meaningful. Okay, so make sure you do that. So that's those are the benefits of saving that in an object. But what if you have the missing data? If you have the missing data, that you can handle those values as a case-wise deletion. So what you can use that here is that use is equal to complete underscore ops. So once you run that, it only uses the complete data set. It's not going to make much difference here because my data set is complete, but you can use that for missing data. But again, if you have questions with the core, just type double question mark and then core. Once you run that, it tells you in here of here, correlation coefficient. Click on that, and learn the arguments that goes with it as well. Okay, and you can run the core dot test as well. Okay, these are all the correlation. Okay, so you can run that as well. uh, but what if you want to add the correlation coefficient to the scatter plot? You can do that with the ggpub again. This is an example. You can do so many different ways, but you can install this ggpub already had that install. Shouldn't have done that. It's a big package, but I already had installed. That's why it's it ended the process pretty fast. But let's just say, if you don't have that, make sure you install that and you load the package. And then with this code, what you are specifying here is that my x is 12 weeks, x variable is 12 weeks prenatal mercury concentrations, y is ADHD scores. I want to add the regression line, confidence interval. I want to have the confidence interval as well. I also want to have the correlation coefficient, uh, which using the Pearson methods. And my I want to give the X lab as a title as this one, and Y lab as title this one. You run the code on GG scatter, and this is what the plot will look like. For instance, is, as you can see now, it also built obviously the mercury concentrations at 12 weeks, ADHD score, perfect positive linear association that you can see from R. The correlation coefficient is 1, and it also prints the p-value as well. So you can also put, uh, you can also uh, print that in the data visualization as well. So I just wanted to show that as well. Okay, now let's learn how to conduct the t-test. Okay, uh, ideally you should conduct the t-test before you run the correlation coefficient, but again, just because, make sure you change the order in your final paper. But again, let's learn how to create the t-test. Now, when you should create a t-test, when you should be using that, make sure you go back to the theory. Okay, but let's just let's look at an example. Remember that one sample t-test, equal variances, unequal variances, there are different sections. We talked about that one, but this is the most common that you will likely use for your final paper, as well as your data as well. Independent two sample t-test for two continuous variable with equal variance, and we assume equal variance in most cases. So what you can do is that you can do the t dot test. You specify your x variable, you specify your y variable, and you specify that there is a equal variances. If that's not true, then you just specify false, and that should be taken care of. But again, it's just, we assume that for most data that it's an equal variances. Okay, you run the t-test and it gives you all these results pretty fast. Just like that, how what is the interpretation here? Interpretation is, for instance, is, remember when we talked about the t-test, we talked about the hypothesis testing as well. So make sure you refer to that if you have forgot about how to interpret that. Here, the alternate hypothesis is the true difference in the means is not equal to 0. What do you think is the null hypothesis? Is that the true differences in this mean is equal to 0. That means that there is no association between x and y. An alternative is that the differences that you see between x and y, the mean of x and y, is statistically significant. So that's what your alternative hypothesis is. It's written in here. And this statistics is for your alternative hypothesis. When you look at that, obviously it seems that there is a, it's such a huge number, it's going to be, the null hypothesis is likely to be rejected. Okay, so with 8 degrees of freedom, the p-value is this one. So it's extremely low, means it's highly strongly statistical significant. And as you can see, this is a 95% confidence interval for this t-test statistics. Okay, and as you can see, it also does not cross this 0 as well. It's highly statistically significant. It's far away from 0. And these are the sample estimates. So this is the mean of x variable, and this is the mean of y variable. Which is the x variable? So this is the mean mercury concentrations at 12 weeks. This is the mean ADHD score. So that means that what t-statistics results are here is that the mean of x and y is not equal to 0, means that there is a statistical differences between x and y. Make sense? So you can do that as well. Like for instance, if you wanted to do, I wanted to do rather than this, I wanted to do data underscore, I want to see if the mercury concentrations at 12 weeks are different than 28 weeks. You can run that as well. So at 12 weeks, the median concentration, mean concentration was 13. At 28 weeks, the mean concentration was 23. So the differences that I see is statistically significant, as you can see from the p-value and the 95% confidence interval. So that means that obviously the concentration seems to be higher, significantly higher, statistically significantly higher at 28 weeks of gestation rather than the 12 weeks of gestation. Okay, so that's how you run the t-test. That's how you interpret that. That's a two sample. It's called a two sample t-test. If you're not too sure what I'm talking about, two sample t-test versus one sample t-test, make sure you go through the theory. Okay, and this is now it's connecting your theory with the lab, and we will do that now you have completed the data transformations, cleaning, and those we will try to connect with this. We will connect all the methods that you will learn in the theory to the lab. Now it's difficult to do with R. Uh, it's easy to do with SPSS, because remember, I think more time, I think the first few labs, obviously, or the many labs, I think, remember, the foundation is difficult to build in. So now remember, I think in just one lab, we are going to, you are going to learn how to do the correlation coefficient and t-test, right? But it takes more lectures for your data set to get ready for that. Okay, so that's the reason why, obviously, as you can see, the labs videos are not that well as well aligned with the theory part. But hopefully this makes sense to you. Uh, so let's we conducted the two sample t-test. You can also specify, let's just, if you want to have the only ones, you only want to conduct the one-sided t-test rather than the two-sided t-test. This is the two-sided t-test that we conducted, two sample two-sided t-test. So you can specify one-sided t-test depending on which side you want to examine, upper or lower tail you are interested to examine. Again, go back to theory, we talked about that. And you can also change the significance level with the dot level argument as well. So you can specify, again, you just want to have your alpha at 0.05, like 95% confidence intervals. But sometimes if you, for some reasons, if you want to change that to 0.01, 0.10, you can do that with this argument as well. Just like here as well, you can easily change that with correlation coefficient. You can easily change that to 0.90. Okay, so alpha would be 0.10. So let's conduct the t-test, one-sided t-test here, where I want to examine the alternative on the greater side. So again, this is my variable x, this is my y variable, this is equal variances. I'm assuming that there are the equal variances, and I want to examine only one-sided on the greater side. So that means that here my null hypothesis is mu less or equal to 0. My alternate hypothesis is equal to uh, sorry, not the mu, but the difference is true difference in the means. So x bar minus y bar is x less or equal to 0. Here the true difference is, alternate hypothesis, that true difference is greater than 0. And as you can see, the p-value is equal to 1, uh, and the 95% confidence is equal to minus 65 to infinite, right? So you can interpret that. Again, this is not an ideal data set to examine the one-sided t-test, but I just wanted to show you that with just one line, one argument, you can conduct the one-sided t-test. Okay, you can also conduct the less as well and run the test. It will examine the another side of the t-test, and as you can see, it's it now your alternate hypothesis is true difference in the means is less than 0. Okay, for most data you will be examining, and again the p-value here is statistical significant, so the difference is indeed less than 0 between x and a y. Okay, uh, makes sense. So this is a way this is how you can do the t-test, one-sided or the two-sided t-test. But again, for most data sets, you want to have two-sided t-test, unless it's there are specific circumstances that where the one-sided t-test might be more meaningful. But again, go back to the theory and also learn about which is a more conservative way. Is the one-sided t-test is a more conservative, or the two-sided t-test is a more conservative? Learn that as well from the theory video. Okay. Um, Now, what if the y is numeric and x is a binary factor? You can still run the t-test as well. So here, for instance, is the t-test here. It's a ADHD score. That's your y variable. Because remember, why it's a y variable first? Because I'm using a tilde sign here. So when you use the tilde sign, your y variable comes first, and then the x variable comes first. So here I'm saying that the sex. Remember, the sex here was binary. Oops. You can, yeah, you can click in here. You can see the sex is a character variable with binary male and female, right? So you can still run the t-test with binary exposure and the continuous outcome as well. And as you can see, the mean, so the mean concentrations of ADHD in female is 73, and in the male it's 73 as well. Okay, so what the t-test will examine, if the difference is of ADHD in the male versus females, if that is statistical significant or not. Here obviously, as you can see, they're exactly the same. So here the alternative, well, the alternative hypothesis here is the true difference in the means is not equal to zero because it's a two-sided t-test. And again, the t-test statistic is zero because as you can see, the means are exactly the same. So the degrees of freedom 3 and the p-value is equal to p-value is equal to 1 because it's 100%. It's not statistically significant. As you can see, the confidence interval also includes or crosses zero as well. So it's not statistically significant. So what you can conclude here, the mean ADHD score in female versus males, they're not uh, statistically different, right? And again, but the more comprehensive interpretation, make sure you go through the theory video. Okay. Uh, so you can run the t-test again, the interpretation, make sure you know how to interpret this uh, from the theory video. Make sure you do that. But again, I just wanted to show you, so learn from the t-test, like from this is called the univariate analysis. Remember, you shouldn't focus too much on the t-test, because if you're particularly, unless you have the clinical trials data where you have randomized the groups equally, then you can interpret that. But again, these results may be confounded by the other variables as well. So this is what we call the bivariate analysis. Bivariate analysis means that you're examining the two variables only at a time, right? Here I'm only examining the ADHD and sex, right? But this relationship could be confounded by, let's just say, age, right? So I would include it there, and that is the reason why the regression models are so important to understand and interpret. So this is bivariate analysis. So when do we use the t-test? We use that for the two continuous variables. You can use that when x is binary, y is numeric as well. Okay, so that's where you can use the t-test for your bivariate analysis. You can also do the one sample t-test. Again, you will not likely use that for your thesis, but again, I just want to show you as well all the codes that are associated with the t-test. So one sample t-test, you can do that as well. Again, we have discussed that in theory at length, so I'm not going to discuss this. But let's just say if you want to examine your null hypothesis, where you can say if your ADHD score is 70 or not. Why 70? Because this is a clinical depending on the score, like if this is a BASC score, behavior assessment school for children, may have mixed up the name. But again, if this is a clinical cutoff point. Above 70, it's considered the child has a ADHD. Less or equal 70, it's not considered as a ADHD. So if that's your clinical, if this is a clinical cutoff point, I want to see if the ADHD score on an average is higher than, or how different it is from 70. So that's why you can run the t-test if it is equal to 70 or not. You run the t-test here, it gives that the mean concentrations are mean ADHD scores are 73. My alternative hypothesis is it equal to 70? That's your null. And the alternative is that is not equal to 70, right? So as you can see, we reject the null hypothesis, meaning that it is significantly different from 70. And again, this why only 70, you can cut off, you can check for any level as well. Like for instance, you can do that for 71. It is still statistically significant. If you do 72, it is likely not significant because it's again 72 and 73, they are close. So like for one-sided t-test, which cutoff point you need to use, it depends on your hypothesis, that which critical point that you want to examine your data with, right? So but you can still do that as well. And again, you can do the one-sided or two-sided t-test as well here as well. You just need to specify the direction along with the mu. Uh, Also, when the data are paired, again, paired sample, you will not likely use that. You will likely use the two sample t-test. But again, if you have the paired data sets, we would have to conduct the paired t-test. Since these data sets are not paired, and it's not a, ideal for For the paired data sets, it returns an error. But if you have the paired data set, this will this code would be appropriate for your data. So what you just specify your x, you specify your y variable, or your two variables that you want to examine, the first one and the second one, and then you just say paired is equal to true argument. Once you run that, it runs the code. But again, this is not the paired data. That is the reason why it gives you an error. Okay, so this is how you examine the t-test, depending on like the one sample, two sample, one-sided, two-sided, paired, unpaired, equal variances, unequal variances, and so on. So, so hopefully this labs video, you have learned how to transform your data sets, final part, uh, and also conduct the t-test and the regression coefficient. And again, make sure you apply this with your final project as you go. Like make sure once you learn this, make sure you do that analysis on your final project as well, so that you don't learn everything at the end of the semester. Okay, so hopefully this helps, and I'll see you in the next video. Okay, bye, take care.